the second half of class. Okay, welcome back to the second half of the robots and robotics class. And so in the first half, we'll talk about, robots. What is it? By definition, what's the origin story and so forth, and how it works under the hood. And we kind of delineate different form of robots. The form that is biomimetic, the form that's humanoid, and all that, right? Especially so how it works. So this is kind of like delineating the different themes. Okay, so the way I did the discussion was, if you think of a robot as creating to serve man, well, you think of a human worker. Okay, what can you count on when you hire a human worker? Okay, so you need this certain thing. Well, what do you need to make a robot function? It's the same question to ask. Okay, this is asked, certain thing. A human gardener can adjust to the terrain, can plan and all that. And there's an analog of all this in robotic form. Okay, so that's how it works under the hood. Now, okay, again, I'm going to embed the discussion, right? So what can it deliver? So let's go to embed the discussion. Again, my plan is to skip this bit, right, and just talk about robotics here. What can it deliver? And this is where your project assignment come in. Okay, so this can be many things. So we can frame this in any way, shape, or form. Okay, but just to emphasize that we understand robotics. Okay, when I say how it works under the hood here, this here, just to make sure, this is not how, say, robotics 101 class would teach you. Okay, so let me add a little bit before I go on. I say, okay, so robotics 101, okay, we talk about physical form. Okay, and that's where mechanical engineering. Yeah, so how it works under the hood. If you talk about like let's do this. How it works under the hood. Human by way of human analog. Okay, by way of human analog. Okay, and so that's a discussion before the okay, and just before we go on, in a robotics class, you study physical form. Okay, use some kind of control mechanism and control and power. Okay, so this would be, mechanical engineering, right? So that you need the arm, you need the joint, you need to rotate, you need to extend, you need to push, blah blah blah. So this week, electrical engineering. Okay, and then the last thing is control, but not control in the same of control movement. So maybe I should say movement control. Okay, movement control, feedback, and power mechanism. Okay, control in this task oriented control. Okay. And this is where you have computer engineering science. In particular, you can go to AI. Okay, AI. Right. So when this is why, you study, you can go, these three majors will enable you to study breakdown in robotics 101. breakdown. Okay, so you study 3 aspects of that. Okay, and just to not to put a fine point on it, if you're talking about say Lego robotics or any kind of Arduino project, okay, you kind of like at this 2 level here. Okay, it's when you add some kind of machine intelligence to it, I think that's when you really get into this aspect. Okay, so let me just do that. Otherwise, you open up a robot's textbook and you say, well, you don't see this thing. Okay, now you see. Okay, so how it works under the hood, that's done, that's taken care of. Okay, so case studies. This is endless. Okay, this is endless, but I'm just going to give you a principle. Okay, then that principle is very simple. Okay, goes back to the definition. 2 things. Oops, sorry. Okay, I'm gonna say 2 principle, 2 overriding, 2 principle. Okay, right. Okay, business case 1 is take advantage of the human likeness. Okay, obviously this principle only applies to humanoid, and not only humanoid but very lifelike. Okay, or at least has emotion. Why? Well, think of it this way. You can have a vacuum cleaner or a vacuum cleaner with a smiley face, right? So one principle is to take advantage of the human-like. So this is the robots that we see in movies, okay? Take advantage of the human likeness potential, of the potential for human likeness. In all form and implication. Okay. Okay, that's one principle. What's the other principle? The other principle is to go back to the original conception, which is, again, utilitarian. i.e., okay, application that humans, and then I'm just going to copy from the definition. Where's the definition? The definition. What is it? What's okay, so I'm going to copy that. Okay, that's it. That's it. So in this case, now I'm with this principle, I'm going to break down into things like, you know, well, economic case, precision, the need for precision, repetition, the need for strength, load bearing capacity, and this is the need to get things done cheaply, economically. Okay, so obviously this is where you get to things like, so if again, some of you are working for the health track, right? So the difference between a robot that a function that say generates or allocate drugs to elderly patients versus a friendly robot that comes to the elderly care's home, and so, you know, good morning, this is your morning pill and blah blah blah. So that would be here. Okay, that's the principle of, so where can it take us? You know, what's a business case? So any kind, you want friendliness that is not done by humans, okay? Right? And the other case is utilitarian, okay? So things we done cheaply hence economically, right? So obviously no one can mass produce automobile without industrial robots. Okay, that's it. Mass produce. Okay, so that's it. And this is IE, medical, surgical, robotics, right? And we don't have to talk about. And this is, of course, same here. Right, industrial robots. Okay, and the need to what? Not use human. Okay, the need to not use human. There's two cases here. One is nuclear disaster, cleanup, rescue, cleanup. So any kind of this disaster, it doesn't have to be disaster, cleanup, nuclear, e.g. nuclear meltdown, earthquake. Okay. What else? Where else do you have the need to not use human? Come on. This is very live, very topical today. Military application, right? E.g. reconnaissance. I can't spell this word. Okay, reconnaissance, right? Okay, and tactical mission. Reconnaissance, tactical mission. Okay, with live order. Okay, so basically with bombs, right? Bomb disposal. So tactical with live. So if you're doing, well, in this case, it's, you know, basically attack. Okay. It almost goes without saying. Okay, you don't. So if you're doing tactical mission without live command, that means reconnaissance. Okay, so reconnaissance mission, bomb disposal. So maybe I put reconnaissance and tactical. Okay. Okay, so that's it. That's why. So you see this, right? So Bayraktar. So if you see this picture, right? First of all, by the way, do you know why it's effective? Well, there's a reason why military drone is effective. I'll give you 3 cases. Okay. Say the case military drone. Say yeah, I'll just say Bayraktar TB4, TB2. Bayraktar case study. Bayraktar TB2, right? Well, any kind of military drone, that's just military attack drone. Okay, why is it important? Why is it so effective? Number one, loiter. Okay, so military attack drones, not only it certainly doesn't risk. So obviously, okay, avoid human casualty. Okay, that's obvious, right? That's obvious advantage. Consider the advantage of military attack drones. Okay, avoid human casualties. Okay, this is very good. Long loiter time. Okay, and low signature. Because it doesn't have to carry a human being, it can be much smaller. It's harder to detect, it's harder to shoot down. Okay, for example. Okay, so something like this, low radar signature. Okay, even visual. Okay, visual radar signature. So long loiter time, right? And some of the attack mode is it's just just flying around doing reconnaissance, right? And then once it identify a target, turns into a bomb, something like that. So avoid, okay, low, okay, and there's probably more, okay. Now there's some disadvantage about psychologically or ethics and so forth and blah blah blah. Okay, the need to, so this is where the payout comes in. Okay, so how do you identify? Okay, again, you are trying to take advantage of technology, making a business case, right? So think of it as wherever you need this load bearing capacity, strength. Okay. Okay. Avoid need for load and capacity. While keeping flex and dexterity. Simultaneous. Flexibility. And that's why, so this is actually to distinguish from say a crane. Okay, a crane is not doesn't have high dexterity, doesn't have flexibility. That's what it is. Okay. Okay, right. So this is where you can imagine. Remember, you're trying to learn the technology so you can benefit from it or build business case. So the question to ask, where is there? Okay, so I can do this. I can say, where is there need? Let's do that. Where is there? Okay. So I turn this into question form. Okay. Well, you get the idea. Okay, so that's it. So the question you have to ask yourself, okay, and where is there need to not use human? Okay, so that's the upshot. Now I'm gonna finish my part because I want to get started on a little bit of a student project that we start with maybe 5 students. We can't cover all the students. Okay, so Now I want to go to over from here. I want to go to here. How will society or social construct evolve? Well, in this case, it's kind of like funny, actually. If you think about it, and this is very important. This is very important. Okay. Robots. So far, I've been talking about utility. Serves human being. Serves human being. Okay. Serves human being. How it's so again, the premise of RUR is creating something mundane. It's in the name. Okay. The name, if you look up the Czech word for robot, I think if you have a Czech dictionary for robot, it would translate to something like mundane, tedious, or something like that, boring, or serving, or repetition. I think the key word is repetition. Okay. So the word robot in Czech means something like repetition. Okay. And yet, when it gets to human society, we take it all the way to the end. If we have robots, we add AI to it, someday it's going to kill us. So that's why you get this. You get this three literature. Well, that two story. One, Terminator. Okay. In this case, robot itself is not turning against humanity. It's the Skynet turning against humanity. But it's using robots to execute the will of Skynet. Okay, so it is an AI gloom and doom, but you can say that, yeah, it's intricately linked to robots. So robot will turn against human. Okay, robot returns against human. Second, robot will try to get love. Okay, or robots will try to be human, and then we talk about human rights. Is it okay to kill a robot, right? So human rights will be robotic rights, right? And then what if the robot fall in love with a person? Can you love that sort of thing? So two themes. One is it's going to destroy us. It's going to want love from us, and this is kind of like putting the two together. Ex Machina is another good film. It's sort of like about love, but using love to destroy us. So basically, the AI as embedded in this humanoid robot. Okay, the story would not work if the robot is not sexy. So the robot has to be sexy to carry out its mission. But the mission, a bit like Terminator, is devious. It's turning against the captor, the human creator. Okay, but it's manipulating the love mechanism of human being. Okay, so is the AI smart? So how do you know the AI is smart enough? Well, when it's smart enough to be manipulative and use its greatest asset, which is its sexiness, feminine appeal, to lure this guy character, the main character. I don't know what the main character is. I think. Yeah, so this girl is using like AI, is luring this programmer Caleb. Okay, so that's the story. Now, the funny thing is, and this is my last comment for today, is that, you know what? If you go back to RUR, that's actually the plot twist. In a good act, there's always a setup. There's also then there's a conflict or something that happened, and then there's a resolution. When the second part is the plot twist. What happened is, remember RUR? Oops. RUR is short for. Oops. ROR is short for this, Rossum's Universal Robot. So Rossum creates robot to do the task. The word, so repetition task. The word universal suggests that it's not one task. So it's not making coffee, it's not vacuuming the floor, it's making coffee, vacuuming the floor, doing the laundry, cleaning the house, all kind of stuff. So it's universal job. Tedious, you don't want to do it. Rossum created something to do it. Well, it turns out that once he created this thing, he sells it all over the world. Let's say, the plot I haven't set to the whole thing, obviously. But essentially, some other scientists thought that, it'd be better, since it takes a human form, maybe it'd be better for whatever reason to add some feeling to this. So it's kind of adding AI basically. Now, it could be originally because if to communicate, right, by instruction. Now, think about it. Human beings sometimes don't communicate by instruction. Human communicates by expressing emotion. So if you bring a hot cup of tea to your girlfriend, okay, she's or if she say, "Oh, I'm so tired," okay, she's not saying, "Go make me a cup of tea," but you sense that she is really tired. She doesn't feel well. She could use a cup of tea. Okay, so that means there's a communication. There's an expression of distress from your girlfriend. She's tired today. She expressed it. You can detect it. Or conversely, you are trying to please your girlfriend, right? So the feeling now comes from you. You want to please your girlfriend, so you buy her flowers, you make her dinner. She doesn't have to instruct you to buy flowers or make dinner. Okay, it's your feeling trying to please makes you perform your job even better. Well, you can imagine that if this guy is endowed with feeling, okay, and this guy can express pleasure or displeasure, then this robot can do a better job by trying to please him, trying to get some kind of positive pleasure from him. So if he smiles, then he's doing a good job. If he frowns, he's not doing a good job. So you can make a machine better if it has ability to interpret, and in this case, manifest emotion. Okay, so that's the second part, second part of the play. Okay, I don't know, I don't know, I think it's 3-act play. Anyway, so that part is like endowing the machine with feeling, and definitely ability to detect feeling from human. So it's ability to detect from human and also have its own feeling. So that's the plot twist. Is eventually it gets tired of this guy, he's just bossing me around. So this robot takes over the world. So it turns out that this doom and gloom Terminator is not a late, 1980s doom and gloom view. It actually was originally in the second, or in the conflict plot twist part of the original play. I don't know what the resolution is. I don't have much to play. Okay, but it's actually, so it's from, so you can think of it this way. The word goes back to that play, but robot really takes off here. Industrial usage, useful. But once it gets useful, human imagination say, "Oh, it's going to kill us one day." The funny thing is that it will kill us in one day. It's actually the plot twist of the original play. So that's kind of interesting. So you can see that human being, again, takes any kind of innovation. Long story short, human beings will make anything about themselves. Yeah, first of all, robot is created to serve human beings. But now we turn it about ourselves, first by saying that, it will take human-like form. It will be like us. It will want to share things with us. It will want to take us on a date. It will want to get married with us. And eventually it want to kill us. So that's kind of funny. So that's how the society evolved with this concept of robotics. Now, the idea here is a little bit going to get a bit messier and messier. I'm not going to go into it right now because we're almost running out of time to discuss student project. But think of this. Okay, think of this. Think transhuman 2.0 will, okay, embed, certainly will embed something like this. Nanotech. It will embed what? It will embed certainly genetic engineering. And of course, it's going to embed what? for sure. Okay, for sure. Okay. So at some point, all the ethical implications going. We actually have this right now. We can. I think you can have look up something like robotic insert to help people walk again, something like that. Well, this is exoskeleton. You can have endoskeleton. Okay, so I should put the word endoskeleton. Okay, exoskeleton. There's actually endoskeleton. I don't know where it is. Maybe it's this video. Okay, exoskeleton is like in movies where you have a this is exoskeleton. This is to help people with disabilities. It's also going to help military infantrymen, you know, who has to carry big stuff like artillery shells or whatever. Okay, but there are also endoskeleton that actually activates the nerve inside the muscle. So the muscle is not dead. It's the neural control, but that's a little bit more like AI than robotics. So that's okay. But this is good. This is good. So let me put that in the resource part of the class. Class 11. So that's good. Okay. Right. Now, this thing. Okay, this thing. Remember, I'm covering this robotics in a way to prepare you for two extreme. One is Dr. Tana, who's gonna be here himself. The other one is this thing, right? This is what some of you may have missed. So that's this. Okay, so I'm gonna walk through real quick. Hold on.
Today I will.
So let me make it large.
To answer some hypotheses from.
So this is the talk.
That's what we call
right.
So basically, that's.
เสียง okay ไหมนะ Okay. Anyway, so this guy's not this guy. This professor, he's very young, by the way, takes inspiration from nature, and nature, you know, has evolved very good solution. How do you? The dung beetle is a very efficient way. Okay, it's actually walking backward. Okay, so he creates robot that does this. So in the first part of the talk, the human-like or the nature-like is more about AI. Okay, but then he gets really interesting into this bit. So this is very active. I think this could be his work or his students' work at BizTech, right? So robot that sort of like creepy crawlies. So there's some efficiency about the way cockroaches move, locomotion. Okay, very low, very stable, very flexible, and works on uneven terrains. And you know, okay, so this thing again, this bit is again, it's more like the AI part of it. It's about planning. Okay, but so the inspiration here is more like AI inspiration. So this is not really, technically speaking, what he's talking about here is not biomimetic. The biomimetic part comes in from the form of this robot, not the algorithm here, but the form. Okay, so this form here is biomimetic. He talks about let's move it a little bit further. Okay, so this is about memory retention. Okay, so the cat sees this, keeps in mind that there's an obstacle. When the cat goes over here, the cat is not seeing the obstacle but avoids it. So again, this is you can say more like AI part of biomimetics, but most of the biomimetic part will be in the physical form. So let's move that along. Let's move that along. This is very good. Brilliant. Okay, and this is extremely interesting. Okay, there's a paper here, by the way, that you can download, and I have it. I haven't read it, but this is what happened. Okay, I wish I can zoom this bottom half. You can see this. Okay, this here, this here is human engineer. This here is human engineer. Okay, so go back to here. Go back to application. Go back to application, right? Okay. I can't find it. Anyway, so this is human engineer. This is a structural engineering solution that came from human. Nature has her own solution. It turns out that nature's solution has non-perpendicular, or this is pretty much like building a truss from 90-degree angle. Well, it turns out that nature uses acute angle or obtuse angle. In other words, very flexible in the way the angles are arranged. So one, he gets, or these two people, maybe his students, get inspired by the nature's way of optimizing the geometry. Then he takes this further, and that's now the new optimization now is done by computer, not by nature, but takes this inspiration and create this kind of fin ray structure that is not based on perpendicular joints. Okay, I don't know if there's a picture of it here, but basically you can say a similar kind of research in YouTube. You can see similar kind of research, something like auto suspension optimized by AI is organic. Okay, see, it's a little bit like this. If a human being engineers, it's going to look like a space frame. It's going to look like traditional space frame. Traditional space frame. Okay, it's going to look like this. By the way, if you study engineering, this is one of the key things that you study. This is done using finite element analysis. See, just straight edges everywhere, right? But if you get inspired by nature and let this flexibility form comes in, this flexible form. So this is kind of like this similar research to what the talk was about. See, this looks very organic. This is not done by nature. It's inspired by nature, but it's optimized by allowing this degree of fluid form. Okay, so the computer is doing the generating the design, but the freedom to make this kind of curve came from nature. Okay, I mean, in other words, you wouldn't have thought as an engineer to start making things like this, but when you look at nature, you get nature's inspiration and you do that. So that's the talk. Oh, let's go back to that talk. Okay. Okay.
Journals and
right.
this.
There. That's the result. Okay. You can see that it has a very organic looking angles, and this is very good for, say, walking on pipes. Now, why is this important? Because this professor, again, he has two positions, right? One in Denmark and one at Vistech, and Vistech gets a lot of well, Vistech is funded by PTT, and huge chunk of it by PTT EP, which is PTT is like a holding company, right? It's a holding company, but the real operation is PTT OR, PTT Chemical, PTT Exploration and Production, so PTT EP. Well, in exploration and production, they have to get oil or crude oil from under the ocean, right? And you have to have pipelines and all that. This is all under the ocean. So even to inspect that, are you going to use human diver, right? So you have two options, okay? You have remote control vehicle, basically submarine that kind of like swims along the pipe and inspect. Now this has its own problem because the current just shakes it everywhere, right? Move it up and down. So it's going to lose track of the pipe. You can have something is more tactile, meaning robot itself can latch onto the pipe and crawl. So it's going to maintain contact at all time, basically, with the pipe. So it's not like an underwater rover that's sort of like a swimming submarine that travels along the pipe. When you get a huge current or fish knocks it or whatever, it's just going to go out of kilter. But here it actually connects with the pipe. Well, the pipe is a round thing. It's going to be very difficult to grab it with something that's not flexible. So you need some kind of flexible yet strong. So this flexible yet strong, nobody does flexible yet strong better than nature. Nature is the best at this job. Okay, the bird's feather, our bone, all kind of stuff is best at optimizing flexible yet strong. So any kind you have, so this word here, this thing, I said the application, right? The application use case, two principle, right? This here. So that's, I put another word, flexible or strong yet flexible. Okay, strong yet flexy. Okay, so it could be very not so flexy, that's the industrial robot, or something extremely flexy. Okay. Very flexible robotic grasp mechanism. Flexible robotic grasp. Okay, so grasp. So this is it, flexible robotic grasp. This is what you see here, this thing right here, and that's inspired by nature. Okay, okay, the more creepy crawlies, more stuff, and this is the neural control. This is actually AI now. So you can think of this as being inspired by nature because, you know, the movement form that looks like a cockroach, right? But you can also get inspired cognitively because a cockroach can move, can sense environment without a big brain. In fact, cockroach, you know, you can take the cockroach and take its head off and it would not die until it starves to death. The reason you chop the cockroach head and it's still running around is because the brain, the neurons are embedded in the legs as well. Okay, so eventually it dies because the head is where the mouth is. Okay, it's not because where the brain is. It has no problem. It has brains here, here, and here, and here, and here. Okay, now, but the control mechanism here, this is AI, this is machine learning. This is kind of my stuff here, more or less, not my stuff directly, but more my area than this, certainly. Okay, and this is the form, and this is to give it a different task to it and so forth, right? And another thing I haven't covered here is swarm robots. In other words, robot that communicates with robots, but you know, that's you get deeper. Okay, this is a very good. This is the dung beetle. I want you to see this picture. See, this is literally copy from nature. Front legs, back legs. Even the number of legs are same. I think 1, 2, 3, 6. Yeah, 1, 2, 1, 2. Okay, 6. So literally, this robot is the work by this. So these are probably his students. Okay, his students. Okay, I think he has students, Ph.D. students at the Vistech as well. I think this guy, I saw briefly the picture. It's a Chinese student. Okay, yeah, this guy is a Ph.D. student at Vistech. So dung beetles. Okay, so the form and the algorithm, and here is talking about some kind of very clever discovery where the robot, you know, does this route, but when it goes home, it just takes a direct path. That makes sense, right? You have to go here and there to do certain thing, but when you're done, you want to go home, you don't have to reverse the path, you just go back or something. So this is something. So if you watch the video, there'll be like paper quotes here and you can download most of them. There's a paper that's coming out that's not publicly available yet from this talk, but I've asked the guy, this professor for it. I haven't got it yet, but okay. So this is okay. So that's that.
And then the mobile robot will come faster. Mobile robot will come from the understanding from the communications, and then over generation. Anybody would like to ask a question?
Okay, so that's that. Okay, so I really encourage you. You know, some of you may have seen it the first time. I did ask him some question a long time, but we had to answer offline a little bit because we didn't have time to answer online. So go to this, and in fact, his research group is here somewhere. Where's it? There. Okay, it's very good. A lot of morphological shape, right? Sensor, neural. So this is more like AI. Okay, this is more like neural control. Embed system. This is closer to a lot of you guys who are doing the smart city track, IoT, that sort of thing. But certainly the bulk of the work is here. Mechanism, muscle models, smart models. Finally, let me mention there's this big area that is not mentioned here, and that is called how it works. Where is it? Okay. So this kind of biomimetic, right? The form, what is it? Robotics and origin story by way of human analogs. Okay. There. Text form. Okay, this is human, so we don't want this guy. We want this guy. Okay, not humanoid. Okay. So this here, okay, this biomimetic, okay, you can say that there is another thing that's called kind of like in between, and I haven't mentioned it directly. It's called soft robotic. So soft robotics is, in a way, is biomimetic in the sense that it's copying the natural flexibility of nature, but it's not, you know, it doesn't have a sort of like a natural analog. So this is a big area, and if you can spare the 3 hours of your life, and I think you should, this is worth it. There's a YouTube podcast on soft robotics. YouTube soft robotics. Lex. This guy. Okay. Oops. I think that's an ad. So let me turn it off. Okay. Lex Friedman is not the creator. He's like a podcast person. Okay. So this is a podcast by this guy. But the guy who does this is this. This guy is very big. I think he works on the lab in MIT. So let me add that to the resource page. That's my resource page. Okay. Class11. This is huge. Oh, sorry. Soft touch in robotics. Yeah, that's it. Okay. And this guy is a very brilliant guy. Yeah. And the area of soft robotics is huge. It's huge. Okay. So maybe I can just soft robotics a little bit. So that's the smart guy. That's the guy being interviewed. But you can say something like here, soft robotics. How soft robotic is changing clothing. So for example. So let's go. When you see soft robotics video, a lot of time will be biomimetics. So for example, this one is imitating worms or something, I think. Okay. Soft robotics. And then there is something that I'm going to mention, but this is a little bit way beyond that. And that is nanorobotics. Okay. But I'm just going to add here just for completeness. Nanorobotics. Maybe, yeah, maybe something like this. This is good. Cold fusion is always a good site. But again, use this as a starting point. Don't just end here, but you actually go down here and read the research and then dig further, right? So let me do that. Cancer killing nanobots. Okay, but that's more like well, it's not out of the scope, but it's very difficult to understand because it's actually nanotechnology plus robotics. Okay, and it's very hard because it's nanotechnology. You can't send computer control. You have to signal it with something else like infrared or electromagnetic wave or some kind of signaling device, chemical signaling device. So it's not, you can't just do robotics. Okay, but certainly soft robotics. Now, soft robotics, I have told many people as I can tell, is the future. Okay, it doesn't matter if you talk about healthcare, manufacturing, soft robotics is really the key future. And you can embed soft robot. You can say which is bigger, right? You can say within soft robotic there's biomimetic, or you can say within biomimetic. But basically, you know, I put them as two separate concepts, but they kind of interlink. Okay, so with that, we have about 15 minutes left for student project. So let's randomly get someone. Okay, maybe we'll stop the video here and